welcome back to our series on practical reinforcement learning with Python. This begins a new chapter, and in this new chapter, we're going to focus entirely on a class of algorithms called the Multi-Armed Bandit algorithms. And there are different variants of these algorithms. So this entire chapter is going to be dedicated to the different algorithms, and we will study the advantages and disadvantages of all of them in subsequent videos that follow. But if you are somebody who have been to a casino before, then you are familiar with this image you are seeing on the slide. It is called the slot machines. Okay, so the idea in a casino is that you put in some money and then you pull levers on each of these machines. Now each of these machines have been configured to have different probabilities of rewarding you. So it could be that for the first machine, the probability that you get a reward is 0.5, which means that it's 50-50, you either get a reward or no. The second machine might have a probability of, let's say, a reward probability of, let's say, 10, which is 0.1. So most of the time you're not getting any reward from this machine. And the reward probability for the third machine might be, let's say, 0.75, which means 75% of the time you are getting a reward from this machine. Now the problem with the way the casinos operate is that you have a limited number of times to pull the levers of each of these machines, and so you are caught between trying to learn the reward probabilities of the different machines and actually leveraging that information to constantly or often pull the lever of the machine that has the highest probability of reward. Okay, and this is a very classical simplified machine learn this is a very classified simplified reinforcement learning problem, and these multi-armed bandit algorithms have been well studied enough, and they've proved to be useful in such situations where you need to take actions based on uncertainties. So like I explained on the previous slide, over here you have slot machines, and then each of them have unknown reward distribution or reward probabilities, and it is your task as a player to maximize how much money or how much reward you can get from these machines in a limited number of steps. So on this slide I am showing 4 machines with different reward probability. So for the first machine, the success rate or the reward probability is 70. For the second, it is 30. For the third, 55. And for the fourth, 40. So your task is, as a player of this game, is to study how frequent these machines reward you, and then you pull them or you play them as often as possible so that you maximize your rewards. Okay, so that, like I said, brings us to the classical multi-armed bandit algorithm that has been well studied enough. So like I said, it is a set of algorithms that helps us to make decisions under uncertainties, and it is simplified to avoid the complexities of reinforcement learning. So there are other environments where this algorithm is not going to be adequate enough to work in such environment. But for such task where you are made to take actions based on uncertainties, then these multi-armed bandit algorithms come into play. So the reason why this is simplified is, for example, there are no delayed rewards. Like your focus is on immediate reward. So anytime you are pulling the lever of any machine, you have the hope that you have done the right job of pulling the most rewarding machine, and so you expect to have your immediate reward right away. And like all other reinforcement learning problems, the goal is to maximize the sum of the cumulative reward. So you want to be able to leave the casino with as much money as possible by pulling the most rewarding machine. Okay, now there are other strategies. For example, this MAB algorithm is applicable when it comes to running advertisement online to determine which design is best. Okay, and there's a classical approach where people do A/B testing. So in A/B testing, they segment their users into groups, let's say two groups, so group one and then group two, and then if you have two designs of an advert, you show one design to one group and another to the other group, and then you study the click-through rate, like how often each of the groups click on the different adverts, and then you use that to inform which ones you should show often to unknown users. But the problem with A/B testing is it doesn't capture changing behaviors of users. It doesn't capture the dynamism in the click-through rate. Maybe there are other factors that affect how often people click on the different adverts. And once you use A/B testing, the A/B testing approach, it is not able to capture the dynamism. But when it comes to the multi-armed bandit algorithm, it is able to capture all these dynamism in the environment. Another example where MABs are applicable is in clinical trials. So let's say a pharmaceutical company comes up with four possible cures of a disease, okay? And these four possible cures haven't yet been tested on humans to know the success rate, like how often they are able to cure their patients. Now, one way of doing this clinical test is to randomly select these medications and then give them to random patients and record how often the medication is able to solve their problems. And then once you have knowledge on which type of medication is healing most of your patients, you tend to um, um, give that medication out more. Okay, so the issue with multi-armed bandit algorithms is that we are trying to solve a problem whose reward probabilities are initially unknown. So like the example I used in a casino, if you go and you stand behind these slot machines in a casino, you have absolutely no idea how often each of the machines have been configured to pay you, how often they've been the reward rate, so like the probability that each of these machines is going to give you some reward is unknown to you, and it is your task to learn this probability and also play. Always keep in mind that you have a limited number of steps, a limited number of times you can pull these machines to hopefully get a reward. And so you need to strike a balance between learning the reward probability distributions and also leveraging the knowledge of the most optimal action to take, so that you take that action more often to maximize your reward. So the agent must keep a balance between exploration and exploitation. And this is a classical dilemma in reinforcement learning. It is called the exploration exploitation dilemma. And it has to do with the agent being able to keep a balance between exploring unknown actions. So, in the casino example, let's say you have played slot 2 so many times that you are confident that this machine, slot 2, has 50% chance of giving you a reward, and you don't know the reward probability of the other machines. Okay, what exploration does is that you randomly select one of these machines whose probabilities you do not know to give yourself the chance to learn. Who knows? For all you know, you are certain that slot 2 has a probability of 0.5 that it is going to give you a reward. What if machine 4 or slot 4 has a probability of, let's say, 0.75? And you do not know because you have not played this machine enough times to ascertain how often it is configured to reward you. So what exploration does in RL is it helps the agent, it allows the agent the space to explore unknown actions. Okay, so you take these unknown actions and then you later learn how well these actions mean to um, um, your future goal, or the number one goal of maximizing your reward. Now, like I said initially, always remember that you have a limited number of actions you can take. I am always going back to this casino example because it is easy enough for us to understand. But in all applicable ways, we assume that we have a limited number of times that actions can be taken. Even if it is continuous, even if you have unlimited steps to take, you still want to explore enough so that you are sure you are taking the best action you can ever take. Okay, so the exploitation step involves the agent leveraging its knowledge of the most optimal action to maximize the total reward. So, what this means is that once the agent has played these random actions enough to learn the reward distribution or the reward probabilities of each of these actions or the slot in the case of the casino, then the agent decides to exploit more. And exploiting means it is going to go ahead to choose the most optimal action often so that it will get a lot of rewards at the end of the day. Okay, now the challenge in multi-armed bandit algorithm is in capturing the dynamic reward probabilities and balancing exploration and exploitation to minimize regret. So, what does dynamic reward probabilities mean? What this means is that the reward probabilities that you know now might not be the same as what you will know in the next step because it will change depending on the action that you take. Sometimes you have not taken the actions enough number of times to actually ascertain what is the most optimal um, action to be taken. So the reward probabilities might be dynamic. There are different environments, and then for some environments, the reward probabilities will be fixed. There are other environments where the reward probabilities might be dynamic. So, what the MAB algorithm helps you to do is to be able to adapt to these dynamism in the reward distribution of each of the actions or the slots in the case of the casino machines. And the other problem, like I explained, is for the agent to keep a balance between exploration and exploitation to minimize regret. So, regret in terms of RL is the difference between how much you could have gotten, like how much reward you actually could have obtained versus how much you got. So if by all means I could have gotten $100 from the four slot machine, but my style of play or the actions I took ended up giving me $60, then my regret is 40 because I could have made 40 more to hit the $100 target. Okay, so what these MAB algorithms does, and I say algorithms because there are variants of them, and we are going to study each one of them in depth, and we are going to actually write code to implement them so we understand. So this is just to give an overview of the MAB algorithm and when it is applicable. Like I said, it is usually useful when you need to take decisions under uncertainties and there are no observations. Like the agent doesn't have to observe anything from the environment mostly. Then this MAB algorithm and its variant becomes very important for you to understand. So in the next video, I am going to show you which areas in real life these MAB algorithms are implemented and how each of the component maps into the physical world. So I'm going to show you if we are using MAB for advertisement, then what then becomes the state, what then becomes the rewards, and how the agent is going to learn. Okay, so once we have this understanding, I will give you an intuitive understanding of the mathematics that powers these algorithms. They are very basic and simple mathematics that once you understand, when you see the pseudocode, you will be able to implement this from scratch. And after that, we will actually get our hands dirty by implementing all the variants of the multi-armed bandit algorithm. So thank you very much for watching, and I'll see you in the next video.